Okay, ShellSort. ShellSort is an extended insertion sort. Insertion sort suffer from bigger dislocated elements. For example, this 0 is supposed to be at here, but it ends up here. In order to move 0 to the right position, it need to do n-1 compare and swamp. So ShellSort improves this scenario by moving the elements faster at the beginning before it applies the insertion sort at the last iteration. So let's take an example. Here we have this array. Instead of moving elements one step at a time, we first move elements 4 steps at a time. So in this case, 0, 1, 2, 3, 4. We compare 6 with elements 4 steps on the left. 6 compare with 3, which is in the right position. We don't need to do anything. In the next iteration, we compare 8 with 2, which is in the right order. We don't need to do anything. In the next step, let's compare 0 with 4, which is not in the right position, so we need to change 0 with 4. This movement moves 0 faster leftward than before. And then let's compare 0 with 4 steps on the left, which has nothing there, so we stop here. Now we back to the insertion sort. Move the elements one step at a time, but the array is better at the starting because 0 is at a better position. Now we do 3 and 2. 2 is less than 3, so let's change it. In the next iteration, we do this subarray. 0 is not at the right position, so let's change 0 with 3. We are not done. 0 need to change with 2. And we finish this iteration. Let's go to the next iteration. This subarray starts from 1. 1 and 3 need to change. And 1 and 2 also need to change. 1 and 0 don't need to change. And we are done with this iteration. We do the next iteration. Start from 6. 6 compare with 3. It's a right order, so we don't need to do anything. Next. 8 and 6 in the right position. We don't need to do anything. So the last iteration, we start from element 4. From 4. 4 and 8 need to change. So let's change it. 4 and 6 need to change as well. So let's change it. 4 and 3 we don't need to change, and we are done. So as you see, by applying a pre-step, our insertion sort work more efficiently because we get rid of those largely dislocated elements. And there is a good sequence for doing this pre-process. Researchers find out the formula like this. So the base case is move one step at a time. Next sequence is 4, then it's 13, then it's 40, then it's 121. Okay, so if we have a large array, say it's 50 elements, we first apply h equals 40 to the first iteration, then we apply h equals 13 to the next iteration, then apply 4 to the next iteration. Finally, we go back to the insertion sort, and the array is almost sorted, and the insertion sort will do its best. So ShellSort is an improvement for the insertion sort. The performance is better, but even today, researchers don't give a particular number. We know it's doing better for large arrays. Okay, so public static int sort The first thing, let's calculate the length of the array. According to that, we can decide the pace. Now go back to the formula. Int h equal 1. This is a base case. As long as h is below n, we can calculate the sequence. Okay. Next step, we want to apply from the bigger to the smaller in the sequence. Okay, now let's do the iteration. Let's compare j is less than its left neighbor, h pace away. Okay, j equal. Okay, for this case, we just want to do the swamp. Okay, that's j, h. Now we're done. Finally, let's return a. This is a ShellSort. Let's copy the same test case. Okay, the array is sorted in increasing order with ShellSort.